everyone. My name is Xun Han from Nebulograph. Today I'm going to talk about GQL and its implementation. This is the first time that I joined an RDBC meeting. I joined Nebulograph in 2022, which is around 2 years ago. So I have around 2 years experience working on graphs, not very long. Before that, I'm working on PoloDB as a cloud-native database from Alibaba Cloud. And before that, I graduated from NTO in Singapore. So during most of my past years, I'm working on optimization databases using emerging hardware. So my talk will be divided into two parts. First, I will introduce our system and product before the arrival of GQL and what we have done to adapt to the GQL, which we think is fascinating for the community. So before GQL, Nebulograph has been an open source distributed databases released in 2018. I think we are probably one of the largest graph database communities, open source communities in China and probably worldwide. And previously, we primarily targeted graph OLTP or latency sensitive applications that is common in internet scenarios or social network scenarios that usually a query does not deal with a very large subgraph. Maybe the number of hops for a particular graph query is less than 3, for example. And we have developed some homegrown syntax that allow users to write their queries for these scenarios. For example, here we have a Go syntax that allows users to specify a starting point and allows them to express how would they like to traverse in the graph from that starting point over some edge types and following some directions and yield the destinations that they have reached in the graph. So this kind of syntax is basically trying to let the users to express how to retrieve some data from the graph by doing some graph traversal operations. And we have, in the internet scenarios and social network scenarios, this kind of syntax it is working, although it's not very easy to use. We do have some compatibility with OpenZephyr that is very good for analytical queries, but we do not have a very full compatibility with OpenZephyr. That is before GQL. So in that regard, our users usually get stuck with writing or debugging graph queries. And this is an example of a user query from our community. It basically has to, the users has to write very complex logics regarding of how they could reach some specific data that they want from a very large graph. And this is a single query that they need to specify a lot of things. And we found this very difficult to write or even to debug. And basically, by simply looking at it, one could hardly has any idea of what is going on. So this kind of queries, once it has been written and tested, it's almost impossible to upgrade or to change it for better performance and so on. And we have this issue with our previous versions that match queries were very slow and due to several reasons. For example, because we are building a graph database from scratch, so we do not always have all the modern and cutting-edge database kernel technologies that other database systems are using for optimal performance. So previously we don't have a very modern query runtime. For example, we do not support concurrent executions for majority types of queries and so on. And we are using very easy data structures without many memory-oriented optimizations and so on. And we don't have much optimization techniques compared with very mature relational databases like Oracle or even MySQL. And in our architecture, we suffer from very high overhead when the user's query has to look up the data from the underlying KV-based storage recursively when they are trying to answer a multi-hop pass query. So this has been the headache for our product in the past 3 or 4 years. So we are always recommending users to write these Go queries because it's easy its performance is better, but it's difficult to write. For the match queries, it's easy to write, but the performance is not good. So in terms of the ease of use for the product, it's not very ideal. So with GQL, we think it's a very good opportunity for our product and for the community. So GQL, we think it is a systematic and standard graph-native query language. So it tells everyone, especially our customer, that the graph databases are serious product. There is an international standard, internationally recognized standard. So this kind of product is here to stay, and you are free to rely on it for serious business. It's not a toy database compared with MySQL or Oracle. So it's going to be serious and can provide you with real values. It's very important. It's also a way for us to, if we could support GQL, we would have a full-fledged language that allows users to easily express their needs for querying a database. That is not possible with our previous homegrown syntax, which is not very general purpose. And with GQL, we can finally implement the idea that users only need to declare graph patterns, path patterns, and so on, and without the need to detail the procedure to get the required data from very large graph, which makes a query very complex and hard to maintain. And with GQL, we see the potential to express both simple or complex graph patterns and graph algorithms in the same language, probably with some further extensions. That is to say, in addition to queries, we think the user should be allowed to express complex graph algorithms using GQL as well, which is different to simple queries. So graph analytic job may usually take a much longer time to run and usually works on a large portion of the graph, probably a large subgraph. But if the users can do this in a single language, it's easier for us to offer both the features for graph analytics and for graph queries in the same product and same system. So that's a very good language opportunity that is allowing our product to reach more customers in the market. It's actually quite important for graph database startups. And our GQL databases product is currently in assay state. We are going to release it formally in 1 or 2 months. And it has the same distributed architecture that we have, that we think has been market proven, at least for our customers. And we separate the computation from the storage. The storage is a share nothing architecture that allows users to store very huge graphs. And in our use cases, our largest storage cluster contains around 200 terabytes of data for a single graph. So that is the case that our architecture is good at, and I think it's something that we can offer uniquely to the market. So we stick to that architecture, but we have a new GQL front end and a new kernel that is allowing faster performance for GQL queries. And during our development, because the GQL language is a new standard, has very many new language features. So we have prioritized the GQL features that is necessary for LDBC queries. So basically, we set the goal to support all LDBC queries as our first language feature requirement goal. So as long as we think we can support all the LDBC queries, maybe we have a good subset supported in the GQL scope. And we are extending our effort to support all the GQL features in our product. And we use LDBC SMB interactive benchmark as our nightly performance regression to test our master branch that we are developing. So basically, my boss tracks our performance for LDBC every morning. We have an automated testing framework that runs LDBC against our code base every night. And every time when our performance drops, we need to explain to our boss that why certain query gets slower. So LDBC has been very important in our developing process. In addition to the interactive benchmark, we found that the BI benchmark is also relevant to the real customer cases that we have seen in the market. For example, sometimes the customers, they retrieve a subgraph from a very large whole graph, and they do complex graph analytics in the subgraph, and they want real-time responses. So that kind of BI tasks, we find it is quite important in the market because people have been increasingly aware of the potential of graph analytics to real-time business decisions. So as an aside, our product is in assay state. We have been offering it for testing purposes for enterprises customers, and it's going to be generally available in 1 or 2 months. So there are some key kernel features that we have done in our SQL databases. First, we have the vectorized and arrow compatible data structure. So Apache Arrow is a good open source data format that that we think is good for vectorized execution, and we have extended to support our graph data storage. We use it to store all the properties and nodes and edges and so on. And we also get inspired by the Apache Arrow code that we support zero copy RPC, both between our computation layer and solid layer, as well as between the clients and our servers. So it saves significant network and memory usages during the RPC stages, which has been a problem in our previous product. We have also implemented the pipeline and vectorized execution runtime like many state-of-art relational databases, which basically divides a query pipeline into multiple independent pipelines that can move the data, flow the data from the source operators to the destinations in independent pipelines and merge them later when necessary. And this is to fully utilize the modern parallel hardware. So this is something that I think almost all analytical engines enjoy in the past, but it's still quite new to the graph database kernels. And in our architecture, so previously we can only push down some scan operators with some filtering to the storage side where we can do near storage processing. So in our current version, we can put an entire sub-query plan to the storage side for computations. So this, on one hand, we can express more fully fledged logics to be executed at the storage side, which is going to be executed by the same code base that the computation layer uses. It can also significantly reduce the network between the computation layer and the storage layer. So this sub-query plan pushdown is nothing fancy, but has helped us to improve the performance and stability of the system greatly. And we are recently developing an in-memory graph where we can either project a whole graph from the storage in memory or create a temporary min-memory graph in the DRAM. So that will allow our users to have very fast graph analytics. Probably you can find some nearly shortest paths between tens or hundreds of pairs of nodes within 1 second, for example, in the min-memory, as long as you have around maybe 128 gigabytes of memory, for example. So we have found that when users want real-time graph analytics, it can only be achieved through in-memory graph-based computations. So we are prioritizing this line of features that is going to support that. So for now, we have around 3 times performance improvements compared with our previous baseline when testing against the LDBC interactive benchmark. And this table will show a brief summary of the speed up. And we have reduced the memory footprint by around 60 to 90% when running these LDBC queries. This is the impact of the vectorized and error compatible data structure alone. We haven't applied any compression or dictionary encoding techniques and so on. So we believe this memory footprint can be further reduced for many data types, especially strings in the future. So our point is that we found it's often a problem for users to deal with very large graphs, be it in memory or not. So it's quite important for graph database kernels to be memory efficient. So we are still working on more projects to make our kernel good for user experiences. So this is a diagram for the lifecycle of GQL query within our system. It's basically the same as any other databases, I think. So the input is GQL and GQL alone, and we do not support any other vendor-locked languages after we have adopted GQL. We have basically abandoned our own homegrown syntax. We think GQL is here to stay, and we want to stick with GQL in the future. We have developed our own parser instead of adopting an open source framework. And yeah, the parser query get translated to AST and get planned and get optimized to execution plan. So basically, the idea here is the same with any other databases, I think. And our execution engine, as I said, is now a pipeline and vectorized execution engine. We allow some, we have done some graph-oriented optimizations. For example, we can push the node IDs when you do a path pattern join. We can push the node IDs and to some scans to avoid full scan or full no scan, and so on. So we have some techniques for that. Basically, the execution engine framework is also the same as many other analytical databases that fully exploits parallelism in the system. And we have subquery pushdown, like I said. So the code base is basically the same. The storage set is ready to process any computations as needed, as long as it can be executed in the storage where it's near the data. And this is the layout of our vector storage. It's quite similar to the Apache Arrow. We do the flattened layout so that the SIMD instructions and batch processing can easily exploit the data. We organize vectors in row groups. That is good for batch processing. And we have zero copy RPC. And language-wise, we have made some extensions in our product, but we haven't proposed these extensions to GQL formally. We probably will do that if when we have time. So the first good extensions that we made is the tabular inserts, which allow users to declare a table using literal values and use GQL queries to insert that into a database. And this is good for batch inserts or batch updates and so on, which is quite common in user queries, and we support it in this way. We borrowed the idea from some of the ideas from the SQL standard. And we think it is important to allow users to match the nodes and edges according to node and edge types, which is different to what is defined in GQL, because that is basically all the matches has to be done on labels. And label is not necessarily correspond to type in the system. But we think the types are important, and we allow users to, instead of using labels, they can use node and edge types to query it as well. And you are free to use labels in the same time. And we have this graph projection and temporary graph features, as I said, which allows users to create a in-memory graph from some data source in the storage. And they can use this projected graph for whatever query and analytical purposes. But the performance is better, the latency is low. So these are some of the graph extensions that we made. We probably will try, if they're good enough, we'll probably try to add it to the GQL standard. Yeah. That's all for my presentation. Okay, I'm taking questions. Thank you.
Thank you. Very interesting. On your last slide, is this working? Oh, you can hear me okay. Yes, thank you. Two observations. I've always thought that we ought to build on the fact that if you have nodes of a given type and they're isolated, they are a table. And that we shouldn't think about having special table syntax. We should think about operating on nodes of that type. Which will achieve the same effect. I mean, there's an issue with GQL because of the fact that tables are actually recognized as a sort of first-class object in terms of, and so there's. But I think from looking to the future, that's just an observation, something worth thinking about maybe. Matching by node and edge type. This seems to me is slightly contrary to the direction that we ended up taking on this issue in GQL, because we put work into introducing the idea of a key label set.
Yeah, I know.
And the key label set with one label effectively identifies a type by a single identifier, and therefore you can query by that identifier, and you have query by type.
Yes.
Yeah. So the issue as to whether, and one of the design goals was actually to avoid changing the query language, to avoid changing pattern matching, so that one could introduce at a schema level that typing capability. You could, and that there would also be at the schema level, at the DDL level, the ability to make that type name under some circumstances. There's optimized syntax to just basically say I've got a name for a type, but it translates. It's a syntactic transformation down to a key label set. So I'm just sort of curious about why, and this is a feedback issue because you've implemented it. Yeah. I'm curious about why that doesn't work. Yeah, or what you don't like about that, because it doesn't mean we did it right. It just means that you've got a different perspective.
Yeah, I understand the logic around the key label set. We are following the GQL standard, including the drafts. There are several reasons. The concept of key label set is, I think it arrives not very early in the drafting process. So by the time that we have seen this logic of making this rationale on determining which types that the user is actually requesting by calculating all the key labels and so on, we have already supported this feature, so we simply did not remove it from our system. And it is our product design principle decided by the company that things we allow users to create node and edge types in their DDL queries, they should be allowed to use this concept that they themselves created. But if you don't want to use it, you want to use the GQL-defined labels and key labels and so on, it's fine, it's supported. But you are free to use this concept that you yourself defined, and it's easy to use because you define these types and you know what they stand for. They correspond to our storage architecture because we organize our storage of nodes and edges according to these types. So this we think will allow users to have a way to understand how this query is executed against the storage. It maybe facilitate some performance optimizations if you have this way to directly use this node and edge types. So from the product design perspective, we choose to have this line of matching added in addition to the labels one. So that's our current setup. Because our system, different to Neo4j, is a strong time system. We are not a schema-less system. We have type and schema everywhere. So we think we should have this syntax because it's aligned with our schema full system principle. So, which is not the case for Neo4j, I think, because it's schema-less. So, but we are the schema full product, so we have this kind of feature. Yeah. Any other questions?
Actually, I do have one other question. It's about your graph projection.
Okay.
Is that simply a subgraph projection? Or do you allow, so if you take the match as yeah, this is like you're creating a view, yeah? So if you take the match as being a way of extracting a subgraph, are you going beyond that? Are you allowing that extracted subgraph to be ornamented, transformed into a completely new graph, or is it basically just wrapping up and thinking about the match result, not as a result table, but as a extracted subgraph?
Okay, there are several issues here. Firstly, we are providing two types of in-memory graphs. One is projection, which means you are basically projecting a whole graph. So you are providing a subset of to some extent of the whole graph, but it's not necessarily a subgraph because we are allowing users to filter some properties or node or edge types that is not necessary for your in-memory task. If we simply project all the types and all the properties, it may consume too much memory. And if you have the knowledge of what kind of properties and what kind of types you want to put in the memory, you can specify them. And we are not going to project them in the memory. So in that case, it's not a complete subgraph because a subgraph will, for each node, it will contain you basically selected some node and edges, and for each node and edge, you have a complete set of properties, which is not necessarily true for a projection because you have the way to filter it. So the concept is a little bit different. We do this because we can allow users to control their usage of memory.
Yeah, no, I mean, I would class that as a subgraph. I mean, it's
sure.
If you do a match and you pull only some properties out, if you drop some type, edge types that you're not interested in or whatever, when by the time you've finished, you've got, a redundant representation of a subgraph, and you can generate a new graph from it, and
sure.
you do that.
Sure. Yeah. So we have a concept called temporary graph, which is the function is more general. So basically, you start from the result of a match query, which has been executed upon some real graph in the storage, and you are free to manipulate the match results. You can add more tabs into it. You can add more properties or remove properties from it. So you can change it to whatever form that you would like, and you can do queries on that. So this new graph would have nothing to do with the original graph because you have manipulated the structure, the schema, and so on. But it will suit your in-memory needs. So that is another kind of graph. And this kind of graph, it does not have any real linkage between the data source graph and the new in-memory graph. So does not have, for example, internally, they do not share the same node ID. Yeah. Although this node could be projected from the original node, it's a new ID.
And just to follow up on that, if you do that, you extract the subgraph and then you start manipulating it in order to create a completely independent graph. Do you use GQL DML on the subgraph that you've extracted in order to change it, or do you have any specific extensions for forming that?
Yeah, we want to use GQL everywhere when it's possible. We don't want to introduce any new syntax, but we found a tiny problem here. But sometimes we probably want to match against an existing graph, but insert into a new graph. I think this is classified as a linear data modification statement or similar in the GQL standard, but in the current version, if I understand it correctly, all the match and insert has to be executed against the same graph. You cannot specify a new independent graph for the insert. We probably would make some extensions here that you can match against some existing graph, and as long as the schema matches, you can insert the data. You can do something with the data and insert it into a new graph. So that would be easier. Yeah, it's natural for this case. So there probably needs some grammar extensions, but the idea is that you can do this. Okay, thanks.
Thank you.